This video is on theory of estimation. This is the first video on theory of estimation. A population is a set of animate or inanimate things about which the study is conducted. A sample is a part of the population, and a parameter is any statistical constant which is computed using all observations of the population. Right? Any statistical constant which is computed using all observations of the population is called a parameter. Any statistical constant computed using sample observations alone is called a statistic. And a sampling distribution is the probability distribution of a statistic. And the standard deviation of the sampling distribution is called standard error. Okay, fine. Now the first property of a good estimator is that it should be unbiased. An estimator T is called an unbiased estimator of the parameter theta if expectation of T is equal to theta. If expectation of T is greater than theta, then T is said to be positively biased. When expectation of T is less than theta, then T is said to be negatively biased. Okay, and the unbiased estimator of sigma square. We know expectation of S square is not equal to sigma square. What is S square? Summation x minus x bar the whole square divided by n. But expectation of capital S square is equal to sigma square, where capital S square is the sample variance x minus x bar the whole square by n minus 1. But this S square is also asymptotically unbiased. It is basically biased, but when n tends to infinity, it becomes unbiased. And consistency, this is an asymptotic property. Okay, according to this property, an estimator Tn is said to be a consistent estimator for the parametric function gamma theta if probability of modulus Tn minus gamma theta is less than epsilon goes to 1 as n tends to infinity. And consistency can be verified using these two conditions. Expectation of Tn is equal to gamma theta and variance of Tn goes to 0 as n tends to infinity. If these two conditions are satisfied as n tends to infinity, you can say Tn is a consistent estimator of the parameter gamma theta, a parametric function gamma theta. The unbiased estimators are not unique. You may have many unbiased estimators for a parameter. And also consistent estimators are not unique. For any one particular parameter, you may have many consistent estimators. So among the unbiased estimators, the one which has minimum variance is called minimum variance unbiased estimator. Among the consistent estimators, the one which has the minimum variance is called efficient estimator. T1 and T2 are unbiased estimators. If the variance of T1 is less than variance of T2 for all possible T2, right? T1 is an unbiased estimator, T2 is any other unbiased estimator. If variance of T1 is less than variance of T2 for all T2, for all unbiased estimators T2, then you call T1 as the minimum variance unbiased estimator. Okay, suppose that T1 is a consistent estimator. This T1 is called an efficient estimator if variance of T1 is less than variance of T, where T is any other consistent estimator. Right? Among the group of consistent estimators for a parameter, the one which has the least variance is called efficient estimator. Okay? Fine. Now, the next point which we should discuss is the efficiency of an estimator. If T1 is a minimum variance unbiased estimator and T2 is any other unbiased estimator of the parameter theta, then the efficiency of T2 is equal to variance of T1 by variance of T2. Similarly, if T1 is an efficient estimator of theta and T2 is any other consistent estimator of theta, then the efficiency of T2 is computed as variance of T1 by variance of T2, right? And some other points which we should remember is if rho is the correlation coefficient between T1 and T2, then this correlation coefficient is equal to square root of E. Okay. With these ideas, let us solve some of the problems today, some of the questions. See, if expectation of T is greater than theta, what would you say about T? T is an unbiased estimator of theta? No, because expectation of T is not equal to theta. T is positively biased estimator of theta? Yes, this is true. T is negatively biased estimator of theta? No, this is not true. None of the above. So, option B is the right answer. If T is an unbiased estimator of theta, which of the following is true? Right? What is given? Let us try to solve this. Expectation of T is equal to theta. Let us consider variance of T. Right? Variance of T is expectation of T square minus expectation of T the whole square. That is expectation of T square minus expectation of T is theta. But always variance is greater than or equal to 0. Which implies expectation of T square minus theta square is greater than 0. Which implies expectation of T square is greater than theta square. So which is true? If T is an unbiased estimator of theta, this is true. I considered variance of T here because I wanted to know something about expectation of T square. So expectation of T square will be there inside the formula of variance of T. So I considered variance of T. Okay. Now let us come to the next question. If T is an unbiased estimator of theta, which of the following is true? Now T is an unbiased estimator of theta, so this is known. Now let me consider variance of root T. Why? The motivation comes from these answers. These answers talk about expectation of root of T. So I consider variance of square root of T. Variance of square root of T is expectation of square root of T square minus expectation of square root of T the whole square. Okay. Now expectation of root T square is T, right? Minus expectation of root T the whole square. What is expectation of T? That is theta. Right? Now variance of any quantity is greater than 0. So I can say theta minus expectation of root T the whole square is greater than 0. Which implies theta is greater than expectation of root T the whole square. Take square root on both sides, you get root theta is greater than expectation of square root of T. That is expectation of square root of T is less than square root of theta. Option D is the correct answer. Okay. Now, which of the following is true? Unbiased estimators is unique? No, they are not unique. For any one particular estimator, you may have many unbiased estimators. Consistent estimator is unique? No, this is also not true. For any one particular parameter, you will have many consistent estimators. Unbiased estimators have invariance property? No. Consistent estimators have invariance property. This alone is true. What does it mean? If t is an estimator of theta, then any function of t will be, t is a consistent estimator of theta. Any function of t will be the consistent estimator of psi of theta. But that is not the case for unbiased estimators. With these two questions, we have understood that point. If t is an unbiased estimator of theta, t square is not an unbiased estimator of theta square. Okay. So, invariance property is there for consistent estimators but not for unbiased estimators. Let us come to the next question. If t is an unbiased estimator of theta, which of the following is true? We have already verified this is not true. This is not true. These are biased estimators because you got expectation of root t is less than root of theta. Right? So, it is not equal to root of theta. Let us try this. Expectation of at plus b. That is a into expectation of t plus b. That is a into theta plus b. So, option A is true. Okay, right. Now, which of the following is true about the sample variance S square computed using observations from normal population? S square, it follows normal distribution, something is given. How to verify this easily? I'll go by a shortcut. We already know about chi-square distribution. Expectation of chi-square distribution is n and variance of chi-square distribution is 2n. But we know ns square by sigma square is a chi-square variate. Ns square by sigma square is equal to chi-square. So, I go with that clue. Right? So, I get n can be taken out, sigma square can be taken out, expectation of s square equal to n, which implies expectation of s square is equal to sigma square. So, expectation of s square, the mean of s square is sigma square. In three options, mean of s square is sigma square. Let us come to variance. Now, variance of ax is a square variance of x. Okay, I am concerned here. N is a constant, sigma square is the constant, s square is alone is a variable. Okay, so n square sigma power 4 equal to 2n. 1n goes off. So variance of s square is equal to 2 times sigma power 4 by n. So what is expectation of s square? Sigma square. And what is variance of s square? 2 sigma power 4 by n. So option A is the correct answer. Right? I go by chi-square distribution, that is rather easy. Okay, the rest of the problems we shall have in the next video. Thank you.